Welcome to part 2 of our discussion of Gauss's law. You remember that last time we talked about some preliminary mathematics that we needed to understand Gauss's law. We had to study surface integrals and divergence, but then we also saw some specific examples of Gauss's law for very simple geometries. So if we had a hollow sphere or if we had a hollow cylinder, for example, those were two examples that we saw. And those hollow geometries, while they're useful mathematical exercises, they will never exist in the real world. All real objects are either going to be solid objects or they're going to be hollow objects but with a wall thickness. I'll refer to those as thin-walled objects, just to recognize the fact that the interior of the device or the object is hollow. The wall thickness could actually not be very thin, but it would still, we want to leave the possibility for there being an empty space inside the object. And we'll be able to deal with those sorts of problems today. Before we tear into the new material, I just wanted to give you a little bit of mention of Millikens Oildrop experiment. This was probably one of the most important experiments of the first half of the 20th century. And it was the first time that we actually proved, that Robert Millikan proved, that electronic charge is quantized. Not only was he able to prove that electronic charge was quantized, he proved the value of that quantization to within about 0.5%. So back in 1909, he knew to within 0.6% the correct charge on an electron. And that's a pretty remarkable thing. And for it, he received the Nobel Prize 14 years later. Okay, let's talk a little bit about solid objects versus hollow objects. Now, the thing about hollow objects, if you see a problem in Gauss's law with hollow objects, you should be happy as a student because it's going to be relatively easy to solve. But as an engineer, you should be unhappy because that's not realistic. There are not going to be real, true, hollow objects in the real world. We need to be able to deal with real objects, which means either a solid object, something like a baseball or a bowling ball, or we need to be able to deal with objects that are hollow but have a thickness to the wall. That would be something like a soccer ball, for example. So when we're working with these, we're going to find that a couple of really important results are going to come out as a result of using these solid objects. I just wanted to point out one real problem with a thin or with an infinitely thin wall is that the voltage is proportional. The voltage is proportional to the derivative of the electric field. That's something we're going to see next time. And while you haven't seen that proven mathematically yet, you understand the concept of voltage, and you would understand that if you have discontinuities in the electric field, which would happen for infinitely thin walls, that would lead to infinite voltage. Now, you can have kilovolts or megavolts or gigavolts, but you can't have infinite volts. And if you ever are doing a calculation in physics and the result that you get is infinite, then you've probably done something wrong. You've probably made an assumption that was too simple, and you're probably solving a problem that is simpler than the real world. And so that's why we're working with, while the wall thickness could be extremely thin, you know, think of like an eggshell. That's an extremely thin wall, but it's not infinitely thin. If you got a very precise measuring tool, you could figure out exactly how thick that wall was. So today we're going to learn how to calculate the electric field in the vicinity of solid objects or hollow objects with a wall thickness that's not zero. Now, I don't really have a lot of new equations for you today. I really just have this one equation that we already saw last time. I guess there is one thing that I would mention about this, that we're going to be getting into some pretty complicated problems today. And when you're knee deep in the swamp, you don't want to have to think about what direction you're facing. So we're going to be looking at a very step-by-step procedure for solving these problems. One observation that I just want to make is that this surface area that's mentioned in the denominator, that is the surface area of the Gaussian surface. There are going to be lots of spheres and cylinders and things floating around. Always remember that A in the denominator is the area, the surface area of the Gaussian surface. And it's only the surface area that is perpendicular to the electric field. So for example, if you had a cylinder, we're looking at the curved sides, not at the two end caps. And so when we're working with the surface areas, it's important to think about which portions of them are going to be perpendicular to the electric field. And the enclosed charge, remember that this is the charge that is enclosed inside the Gaussian surface. So we're gonna see, I believe it is 4 specific multi-part examples today where we're gonna tackle these problems step by step, and you're gonna see some pretty structured ways for solving these problems. But just make an observation of the fact that it's the Gaussian surface. It's the area of the Gaussian surface, and it's the charge that's enclosed inside the Gaussian surface. Okay, most of the rest of today is going to be examples. So let's see the example of an electric field in all regions for a solid charged sphere with uniform charge density, a total charge of Q, and a radius of A. I actually forgot something on the previous page. I just wanted to mention that, and that is that what we want to do is we want to figure out how to break the problem down into all possible regions. So I'll do that for you in these examples. In fact, I've already done it in these examples, but just be aware that if you're doing a problem from scratch, you have to break the problem down into all possible regions. So for example, if you're inside a sphere or outside of a sphere, those are two different regions. Or if you're inside of a cylinder, or you're in the wall of the cylinder, or you're outside of the cylinder, that would be three different regions. And then when you're doing this, the problem for each of those regions, you want to calculate the total amount of electric charge that's enclosed within the Gaussian surface and the surface area of the Gaussian surface. Remember, those are really the only two unknowns in that equation 5.9. Epsilon 0 is going to be a constant, so if you find the enclosed charge and the surface area, you have de facto found the electric field. Okay, so let's tackle this problem in exactly that way. So I'm making an observation here, and that is that the way that this picture is drawn for the first part, r is less than a, and it's a sphere, so we're using spherical coordinates, which is why I'm using r here. And then you can see I've got a dotted line to separate it, and then the second part of the problem is if r is greater than a. So we're either inside the sphere or we're outside the sphere. Again, this is a solid sphere. There is no hollow center to this sphere. It is solid all the way to the core, like a golf ball. So let's calculate the electric field. First of all, we're going to need to calculate a few other things. I just want to make a quick observation here. I'm going to put it up above here so that we don't interfere with any of the other problems. The area, the surface area of a sphere is 4 pi r squared, and the volume of a sphere is 4/3 pi r cubed. Now you might have those on the tip of your tongue, but if you didn't, now they're at the top of the page here. Let's go ahead and calculate what is going to be the charge density that's enclosed inside the Gaussian surface. So how much charge, how much Q enclosed is inside of that surface? Well, I know that this entire sphere contains a charge of Q. And so step 1, I'm going to calculate rho sub v. I'm going to treat this as a three-dimensional object, and so therefore I need the volume charge density. Well, the rho sub v is going to be equal to the total charge divided by the total volume. So I'm going to go ahead and write total charge divided by the total volume. And we were given in the problem statement, and I even wrote it over there on the figure, that the total charge is just Q. Now in a different problem you might be told that it was 2 coulombs or 10 millicoulombs, but here it's just a variable Q. And what is the total volume? Well, this is a sphere, so it's the total volume of a sphere, 4/3 pi. And now what is the radius of that sphere? Well, the radius of the total sphere is a. So this is 4/3 pi a cubed. And then so that is the charge density. Now the second thing that I want to do is I want to figure out what is the volume of the Gaussian surface. The volume of the Gaussian three-dimensional object, if you will. Well, that Gaussian surface is this inner sphere right here, the one that I've already shaded, and now I'm sort of cross-hatching. So the volume of the Gaussian surface is just 4/3 pi, and what's the radius of that cross-hatched region? It's r, so it's 4/3 pi r cubed. And the Q enclosed, this will be step 3, Q enclosed is equal to, and I'll probably only do this one time, but I just wanted to remind you that the enclosed charge is the charge density integrated over the volume. But the charge density is a constant, which means that I can move that out in front of the integral. And by the way, it says uniform charge density. That's how I know that rho sub v is a constant. So this is just rho sub v times the integral of dv, which is just rho sub v times v. And the charge enclosed inside the Gaussian surface, so therefore this is the volume of the Gaussian surface. So I'm just going to take those two things I just calculated. It's going to be Q divided by 4/3 pi a cubed multiplied by 4/3 pi r cubed. The 4's are going to cancel, the 3's are going to cancel, the pi's are going to cancel, and I'm just left with Q, sorry, this is going to go over the picture a little bit, r cubed divided by a cubed. And then step 4, I'm kind of going to run out of room here a little bit. The area of the Gaussian surface is the area of a sphere with a radius of r. So this is 4 pi little r squared. Up here I'm using this capital R as generic, but within the problem statement itself, whoops, there's an extra E in there. Within the problem statement, within the problem solution itself, we have a sphere of radius a, and then we have a Gaussian surface of radius lowercase r. And then step 5, I'm going to calculate the electric field is equal to the enclosed charge divided by epsilon 0 times the area of the Gaussian surface, which is, we have q r cubed divided by a cubed, and then that whole thing divided by epsilon 0 times 4 pi r squared. The r squared is going to cancel with 2 of the 3 r's in the numerator, and I'm left with q times r divided by epsilon 0 times 4 pi a. You know what I think I'll do? I'll call that, let me erase that there. I'm going to have 4 pi epsilon 0, and it's a to the 3rd power. I forgot the 3rd power there. So that's the electric field within the sphere. Interestingly, notice that it increases as r increases. As you get further and further toward the surface of the sphere, the electric field is getting stronger and stronger. So I'm going to erase this cross-hatching so I can draw something in here. The electric field is pretty weak right here, and it gets a little bit stronger here, and it gets the very strongest right at the surface. And if you think about it, if you were right at the center of the Earth, gravity would be pulling you equally in all directions. You'd also be 10,000 degrees Fahrenheit, so you'd die instantly. But if you didn't die instantly, you would feel gravity pulling you equally in all directions. But as you get closer and closer to the surface, you get closer, so more of the mass is pulling you in one direction. It's all pulling you, in this case, to sort of toward the southeast. And the same thing would be true of charge density. That if you're at the center of the sphere, it's going to be totally balanced, and the electric field will approach 0. By the way, you can see that that's the case here, because if r is equal to 0, the electric field is equal to 0. As we get closer and closer to the surface, the strength of the electric field will increase, and that's why the numerator of this electric field contains an r. What happens if you pass outside the sphere? Well, if r is greater than a, then I know how much charge is enclosed inside this larger Gaussian surface. Well, remembering that this sphere contains plus q, q enclosed is just q. That's about as simple as it gets. Some of these parts of these problems are going to be easy, and some of them are going to be hard. What is the area of the Gaussian surface? Still 4 pi r squared, and therefore the electric field is q enclosed divided by epsilon 0 times the area of the Gaussian surface, which is q divided by 4 pi epsilon 0 r squared. And that's actually the same result that we found last time for a hollow sphere. And it's also the same result that we found for a point charge. And so the interesting thing is that if you are outside of the sphere, you don't know or care whether the sphere is hollow or solid, or how thick the wall is, or even if it's just a single point charge. All you know is that there is a piece of charge that exists with a high level of symmetry. Remember that if this were a lump, so imagine if this were like some sort of weird lava pit of charge density, then there wouldn't be the level of symmetry that we would need to solve the problem in this way. But because there is that level of symmetry, we're going to get the same result regardless of exactly how that is distributed across the radius. And then I've taken those two sub results. So this is part 1 and this is part 2, and I plotted them using MATLAB, and this is what it looks like. So I've chosen q to be 5 epsilon 0 just so that the math would work out easier. The epsilon zeros would cancel out. And I chose a to be 2 meters. So let's draw a dotted line here at 2 meters. And you can see that in this region here to the left, in this region, I'm going to have that the electric field is q times r divided by 4 pi epsilon 0 a cubed. And in this region over here, it's q divided by 4 pi epsilon 0 r squared. So within the sphere, so here is inside the sphere, and this is outside the sphere. Inside the sphere, the electric field is increasing proportional to r as you move closer to the surface. There's continuous electric field at the surface of the sphere, but then outside the surface of the sphere, it begins to drop off as 1 over r squared. The most important thing that you should take away from this example is the continuity of that electric field right there. If you're solving one of these problems and you don't get a continuous electric field, you've made a mistake. Okay, let's look at what happens if we have a sphere that is thin-walled. So I'm drawing it here to show that there is a hollow section, but then there is a wall thickness. It starts at A and it ends at B, and then of course you could be outside as well. So there are actually 3 different regions. Region A, or I guess I call it region 1, is you are inside the empty part of the sphere. Don't know why that disappeared. Region 1, you're inside that part of the sphere. Region 2, you're inside the wall. And then region 3, you are outside the sphere. So let's tackle region 1 first because it's the easiest. Region 1, what's Q enclosed? Well, if you look inside that Gaussian surface, there is no charge density. So Q enclosed is equal to 0. I don't even care what the surface area is because the electric field is Q enclosed divided by epsilon 0 times A. And if this is 0, then this is equal to 0. So inside the hollow cylinder, inside the inner wall of the hollow cylinder, the electric field is 0 everywhere, at every point. So it doesn't matter whether you're here or right at the very center, it's 0 at all points. By far the most interesting question is what happens inside the wall. So you'll notice here that in this example, in part 2, the radius r is greater than A, but it's less than B. So you're inside the wall. And this is one of the most detailed examples of this portion of the class. So let's tackle this one first. I'm going to figure out what is the enclosed charge. Well, step 1, I'm going to calculate what is rho sub V. Well, rho sub V, remembering that this thin wall contains a total charge of Q. Well, that's going to be the Q total divided by the V total. And I hope that after these 2 examples, and we've got 2 more to go, I hope that you're going to see there's a very clear pattern that we're following here. So this numerator is going to be Q. That's the total charge. What is the total volume of the blue region? Well, we could start with the volume at B, which is going to be 4/3 pi B cubed. But the problem is that there's a bite taken out of it. There's a bite out of the middle. And the part that's taken out of it is the volume of radius A. So this would be minus 4/3 pi A cubed. So if you take, imagine now, I'll sort of draw an alternate example here. You've got a volume here, and if you took all of that, but then you subtracted off this portion of it, so I'm going to discount the middle portion of it, I'm going to subtract that part off, you'd be left only with the part that is in the donut. So this is the donut, and this is the donut hole. Okay, we can't really simplify that much further, so I'm going to leave that the way that it is. What is the volume of the Gaussian surface? This problem is pretty complicated, so we're going to take every single step separately. The volume of the Gaussian surface, and I need to mention, this is very important, only the part that contains charge. So let me sort of zoom in here on an arc of the wall. I've got the inner wall and the outer wall, and then here's the Gaussian surface somewhere in the middle. Well, the part that's inside the Gaussian surface that contains charge is right here. This portion contains charge. So I guess I could shade that here as being, in between the dotted line at R and in between the solid line at A. That's the portion that we're accounting for here. And so the volume of the Gaussian surface is going to be 4/3 pi r cubed minus 4/3 pi a cubed. So that's the charge density is step 1, and then the volume of the Gaussian surface is part 2. I'm going to erase this observation here so I have room to do the next step. But just remember that you might have said, hey, the volume of the Gaussian surface should just be 4/3 pi r cubed. And that would have been the volume of the entire, the sphere with the entire dotted line. But remember that this part contains no charge. And so therefore it doesn't get counted. So what is the enclosed charge? The enclosed charge is rho sub v times VGS, which is Q divided by 4/3 pi, and I'll factor that out, and then it's B cubed minus A cubed multiplied by the volume 4/3 pi times R cubed minus A cubed. That's the volume of the Gaussian surface. Cancel the 4s, cancel the 3s, cancel the pi's, and I'm left with Q times R cubed minus A cubed divided by B cubed minus A cubed. And then step 4, what is the area of the Gaussian surface? Well, the area of the Gaussian surface is the easiest part of this calculation. It's just 4 pi r squared. So this is the surface area of the outer surface of the Gaussian surface. And then step 5, what is the electric field? It is the enclosed charge divided by epsilon 0 times the area of the Gaussian surface, which is Q times R cubed minus A cubed divided by B cubed minus A cubed, and then I'll add an epsilon 0 to the denominator, and then the denominator also gets a 4 pi r squared, where that's the area of the Gaussian surface. Let's see, can anything cancel here? I don't believe that anything can cancel, so I think that's about as simple as I can get it. So I'm going to go ahead and leave it like that. Happily, the third part is much easier, because if you're outside the donut, if you are outside of B, if R is greater than B, then the enclosed charge, which is usually the hardest part of the problem, is just Q. You contain the entire hollow sphere, the entire thin-walled sphere, and so as a result, you pick up its entire charge. So that's equal to Q, and the area is still 4 pi r squared. So the electric field is going to be it's Q enclosed divided by epsilon 0 times the area, which is Q divided by 4 pi epsilon 0 r squared. So we've got 3 regions. We have 3 different functions. One of them is trivial, one of them was pretty challenging, and then the third one is something that we've done several times now. And here's my favorite part, is that if you combine those together, and here I've chosen Q to be 5 epsilon 0, A is 1.5 meters, B is 2 meters. This is what the plot gives you. And you may not be able to see it very well, but it's 0 here. And then at 1.5 meters, we have a transition. And then at 2 meters, we have a transition. But notice that the curve is continuous at both of those transitions. It's continuous at the inner wall, and it's continuous at the outer wall. And notice again that when we're within the region of charge density, the electric field is increasing as according to R, and when we're outside the outer region, it starts to decrease as 1 over R squared. That's exactly the behavior that we saw with a solid sphere, with a hollow sphere, and now with a thin-walled sphere as well. The other observation that I would make, notice that the peak value here is 0.1. And if I scroll way back up to the previous example, notice that the peak value here is 0.1. And that's because when you're at the surface of the sphere, again, you don't know whether the sphere is solid or hollow or thin-walled. The exact same observations will take place regardless of the behavior inside the sphere. And so that will include the strength of the electric field right at the surface. Okay, let's talk about cylindrical objects. There's not too much different about cylindrical objects. I'll just make a quick observation here that the area of a cylinder is going to be 2 pi r times L. And sometimes it is 2 pi r times h. My cylinder is laying on the side, so I'm going to call it 2 pi r times L. And the volume of a cylinder is going to be pi r squared times L. So those are going to be good, useful equations to know. So now we have a solid cylinder, and I'm not a very good artist, but I've tried to represent that this is not a sphere, that it is in fact a long tube that's going backwards here. So let's calculate step 1. Let's calculate what is rho sub v. Rho sub v is the total, doggone it. Okay, so I've got to get back down here. So rho sub v is the total Q divided by the total volume. And in this case, the total charge, let's see, I'm gonna block off a portion of this, and I'm gonna call this to be a length of L. And it has a linear charge density of rho sub L. So the total charge that's contained within this cylinder of length L, I guess I shouldn't have drawn it quite that far. So if the length goes to here, then I'm only going to go back that far. This is equal to rho sub L times L. And then what is the total volume? Well, we just saw the total volume. It is pi, and what's the radius of this total cylinder? It's A, pi A squared times L. The L's will cancel, as the L's will always have to cancel. Rho sub L divided by pi A squared. Step 2, what is the enclosed charge? I've sort of blended together calculating the volume of the Gaussian surface. I'll just mention over here, volume of the Gaussian surface is going to be pi r squared times L. And following the example that I had done previously, these should be capital R's because they're generic, and then the lowercase r that's right here is specific to this problem. So Q enclosed is going to be rho sub v times the volume of the Gaussian surface that contains the charge density. So this is going to be rho sub L over pi A squared times pi r squared times L. Well, the pi's are going to cancel, and we're left with rho sub L times r squared times L divided by A squared. And I'm just a little bit nervous that there's still an L in there, but I've still got one more step to cancel things out, so let's see how that works out. The area of the Gaussian surface is the area of a cylinder of radius r. So this is 2 pi lowercase r times L. And then step 4 in this case, again, we didn't have a step 5. I guess you could call this step 2.5. The electric field then is going to be the enclosed charge divided by epsilon 0 times the area of the Gaussian surface. And the enclosed charge, we already found that. We found it right here. Oh, I shouldn't box that one. I'm just going to box the final answer. So it's right there. So this is rho sub L times r squared times L divided by A squared. The denominator also picks up an epsilon 0. That was almost the wrong Greek letter. This is epsilon 0. And then what is the area? 2 pi r L. Oh, good. The L's canceled. This r is going to cancel with one of these r's, and I think that's all I can simplify. I end up with rho sub L times, oh darn, because this is cylindrical coordinates, I should have been more careful about using rho instead of r. So let me just go back here, and here this r should have been a rho, and 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 this r should have been a rho. So it's rho sub L times rho divided by A squared times 2 pi epsilon 0. And so that's my final answer for inside the cylinder. And then if I am outside the cylinder, things get quite a bit easier. The enclosed charge is just rho sub L times L. The area of the Gaussian surface, that's going to just be 2 pi rho times L, and the electric field then is going to be Q enclosed divided by epsilon 0 times the area, which is going to times the area, which is going to be rho sub L times L divided by 2 pi rho times L. L's cancel, and I'm left with rho sub L divided by 2, oh, I forgot the epsilon 0. Epsilon 0, so 2 pi epsilon 0 rho. Rho sub L over 2 pi epsilon 0 rho. Excellent. And so you'll notice that up here, the electric field is increasing proportional to rho, but once you get outside of the surface of the cylinder, it's decreasing proportional to 1 over rho. You might say, hey, why was it rho squared in the denominator for the sphere, but it's only rho in the denominator for the cylinder? And the answer is that because the area of the cylinder only has a rho, whereas for the sphere it was 4 pi r squared. So once again, we can plot the electric field, and we see that it's increasing linearly when you're inside the cylinder. So over here you're inside, and over here you're outside the cylinder, and this is proportional to r. Yeah, I probably shouldn't say just that. So it's going to be rho sub L times rho divided by 2 pi epsilon 0 a squared, and then over here it's rho sub L divided by 2 pi epsilon 0 rho. And you'll notice again it's continuous. So that's a good sign of the fact that we have in fact solved the problem correctly. Okay, our last problem for today is going to be our hardest one. Maybe not. I don't know if this one's harder than the sphere was, but we're gonna look at a thin-walled cylinder. So you can see in part one. In part one of the problem, we're going to be inside the inner surface. You can probably do a pretty good job of guessing what that answer is going to be right now. Part two, we're going to be inside the wall. And then in part three, we're going to be outside the outer wall. So those are the 3 parts we're going to look at. For this first one, what's the enclosed charge? I'll give you a second to think about it. The enclosed charge inside that Gaussian surface is 0. And therefore the electric field, which is equal to Q enclosed divided by epsilon 0 times the area, is also equal to 0 because the enclosed charge is equal to 0. Anytime that you have a hollow or a thin-walled object, the electric field will be 0 inside the innermost of those objects, as long as they're symmetric. Okay, here's the hardest part. We're going to do step 1. What is the charge density? This charge density is the total charge divided by the total volume. And the total charge is rho sub L times L, where once again we're going to take a certain distance L, and we're just going to consider that region of it. And that's going to be divided by what is the total volume of this cylinder. Okay, I'm going to take the volume of a cylinder whose radius is B, and I'm going to subtract from that the volume of a cylinder whose radius is A. Sort of like those Russian nesting dolls. We just want the volume of the biggest doll. So I'm going to subtract from that the volume of the second biggest doll. So this is let's see, the volume of this one is going to be pi b squared times L minus pi a squared times L. The L's are going to cancel, and I'm left with rho sub L divided by pi b squared, and I'll say pi times b squared minus a squared. Step 2, the volume of the Gaussian surface. And I'm going to draw it here this time. That contains charge. So the volume of the Gaussian surface is going to be, again, I'll sort of draw you the picture here. It's the portion that is inside the dotted line, but that contains charge. And so that's going to be this portion right here. So the volume of the Gaussian surface that contains charge is going to be pi times rho squared L minus pi a squared L. So this is the size of the outer doll, and this is the size of the second largest, or this is the size of the donut, and this is the size of the donut hole, but now it's a cylindrical donut. And then step 3, what is the enclosed charge? It's going to be rho sub V times the volume of the Gaussian surface, which is going to be rho sub L divided by pi times b squared minus a squared multiplied by pi L times rho squared minus a squared. The pi's are going to cancel, and I'm left with an L there. This could be rewritten as rho sub L times rho squared minus a squared divided by b squared minus a squared. The area of the step 4, try that again. Step 4, the area of the Gaussian surface is just the area 2 pi rho times L. That's the area of a cylinder whose radius is rho and whose length is L. And then step 5, the electric field is Q enclosed divided by epsilon 0 times the area of the Gaussian surface, which is rho sub L times rho squared minus A squared, all of that divided by B squared minus A squared. So all I did was I took the charge enclosed. Hold on just a quick second. Yes, so I messed myself up by doing this. So I'm just drawing this. So here, this Q enclosed right here just goes down to here, and then multiplied by, I need to put an epsilon in the denominator, epsilon 0, and then I also need an area of the Gaussian surface in the denominator, so that's 2 pi rho times L. The L's are going to cancel. That's always good news. And nothing else cancels. So I'm left with rho sub L times rho squared minus A squared divided by 2 pi epsilon 0 times rho times B squared minus A squared. And that looks like a pretty complicated function, but remember that A is a constant, B is a constant, 2 pi is a constant, rho sub L is a constant, there was another, epsilon 0 is a constant. So the only thing that is variable in that equation is rho. And the only dependence of rho in that equation is in the denominator. And by now, I hope that you can get this one. Q enclosed is rho sub L times L. The area of the Gaussian surface is 2 pi rho times L. And the electric field then is Q enclosed divided by epsilon 0 times the area of the Gaussian surface, which is rho sub L times L divided by epsilon 0 times 2 pi rho L. L's cancel, and I'm left with rho sub L over 2 pi epsilon 0 times rho. So we've got 3 regions. We have 3 functions for those 3 regions. 0 inside the inner sphere, pretty complicated function in the wall, and then a relatively simpler function outside the wall. But notice that if you look here, there's a rho squared in the numerator here, and there's a rho in the denominator. So it tends to increase. It won't necessarily increase linearly, but it will tend to increase in a somewhat linear fashion. Whereas here, the rho dependence is in the denominator, so it's going to decrease according to 1 over rho. And here's the function. And while that may look like it's a straight line in between the 2 walls, it's actually not quite a straight line. So just be aware of the fact that it is more complicated here than it was in the previous examples. Nonetheless, we still have continuity at the boundaries, which is absolutely necessary. And we can see that in general, if you're inside the shape, it's going to be 0. And as you go away, it's going to drop off as 1 over, in this case, rho squared. I'm sorry, no, it's going to drop off as 1 over rho because it's a cylinder rather than a sphere. So the last thing I want to leave you with is this step-by-step procedure. Break the space down into regions. For each of those regions, calculate the volume charge density. So calculate rho sub V. This may also require the calculation of the total charge and the volume of the shape. Calculate the charge enclosed, which will require the calculation of the volume of the Gaussian surface. And then remember, portions of the Gaussian surface that do not enclose charge are not included in this part of the calculation. And then once you've calculated the area, then you can simply apply our one master equation for these 2 lessons to be able to calculate the electric field density. Remember, the electric field in the vicinity of any realistic 3-dimensional object will always be continuous. It must be continuous. It will tend to increase inside regions of charge density, and it will tend to decrease outside regions of charge density.